Welcome to qnawire.
Hi, so over here we're going to have the following titration of methylamine with nitric acid. If we want to plot the pH with respect to the volume of acid that we're adding, the shape is going to be the following. We're going to have a slight decrease, then something like this, and so on. So at 1/2 of the equivalence point, the pH would correspond equal to the value for pKb for this reaction. Why to the pKb instead of the pK? The reason behind this is that the reaction that is occurring with methylamine with water, well, actually over here with H2O plus coming from the acid, is going to generate the methyl ammonium ion plus simple water. So over here, POH would be equal to pKb. Thus, the value for pH would correspond to the pKa of the acid in question at this half equivalence point. So whenever we have reached the half equivalence point, we have added 1/2 of C0. So at equilibrium, we're going to have the same quantity of the conjugate acid and of the base. So in this case, the pKa for this compound, we can find it online, is going to be equal to 10.6. Thus, at the midpoint of the titration, the pH is going to be equal to 10.6. You just need to verify that this value coincides with the reference link for the equilibrium constant required to you. Remember that the pKa is going to be equal to minus the logarithm of the Ka constant. Now, for the pH at the equivalence point, what is going to occur is a little bit different. We're going to consider still this reaction, but we're going to assume first that all of the NH2 is going to be titrated. Let's say that we have an initial concentration, we have the same initial concentration. So we're going to get essentially 0, 0, and initial concentration over here. For this reason, the next reaction to be considered at the equivalence point is going to be that of methyl ammonium ion plus water to produce H3O plus methylamine, which is going to be directly the Ka reaction. To know the initial concentration, we're going to employ the values over here of methylamine. In this case, we're going to have a 1-to-1 reaction, so the amount of mole of CH3 and H2 that we're going to have needs to be equal to the amount added of the nitric acid. So the initial amount would correspond to 0.272 mole per liter multiplied by the volume, which is going to be 20.9 times 10 to the minus 3 liters, which is 5.6848 times 10 to the minus 3 mole. And this needs to be equal to the amount of nitric acid that we have added when we reach the equivalence point. Thus, the volume that we added is going to be equal to the amount of mole divided by the concentration of the nitric acid, which is 0.342 moles per liter, which is 0.0662222 liters. Now let's compare this with the initial volume of 20.9 milliliters. The volume added is going to be equal to 62 milliliters added, rounded up to 4 significant digits in this case. We can round up to 3 if you want, but this would give us a total volume of 37.52 milliliters at the equivalence point. Thus, the initial concentration of the methyl ammonium ion would be equal to the amount of mole that we just calculated, because that is going to be the maximum amount that is going to be produced, divided by this volume in liters, which gives us an initial concentration of 0.1514 molar. This is going to be our value of C0. So now with this information, we're going to turn back to our equation. For the reaction with water to produce H3O plus methylamine, we're going to write down our ice table, where we're going to have C0, water doesn't enter equilibrium, 0 and 0. A fraction is going to get dissociated, minus x, and plus x. So at equilibrium, we're going to get C0 minus x, and x. The value for Ka is going to be equal to 10 to the minus pKa, so 10 to the minus 10.6. Thus, we can apply the small x approximation. The value for Ka is going to be equal to the concentration of H3O plus times the concentration of methylamine divided by the concentration of methyl ammonium, and replacing the values that we got at equilibrium, we get x squared divided by C0 minus x. Under the small x approximation, this is going to be equal to x squared divided by C0, because since the value of Ka is going to be small, we can assume that C0 minus x is going to be approximately equal to C0. With this, the value for x is going to be equal to the square root of the Ka times my initial concentration that we calculated. So this is going to be equal to, I'm going to plug in directly the value, 1.95086 times 10 to the minus 6. And what this is going to be equal to, well, if we compare it to our ice table, this x is going to be the equilibrium concentration of H3O plus. Thus, the value for pH, which is minus the logarithm of concentration of H3O plus, becomes minus the logarithm of this value of x that we just got. So our answer is going to be equal to 5.71. And this is going to be our pH at the equivalence point. If you want, we can round it up as 5.7 directly. So with that, it would be all. Just verify that the value for the pKa of this acid coincides with the one on the table from your reference. Otherwise, just replace the value and you're good to go. Just follow the same procedures and you should have not that different results. And with that, it would be all. Thanks and have a good one.